It's Paul with the next installment of your mathematical Thanksgiving treat, a 2-page introduction to the fascinating topic of conjugate convex functionals. We need a convex set. How about the closed interval from 0 to 1? Certainly, if you join any 2 points in that interval by a line segment, that line segment lies entirely in the interval. And for a convex functional, we will use the functional x squared, but its domain will only be the set C. Now let's think about the dual space. We can represent this dual space in a fancy way by saying an element of it is a linear functional x star which acts on x, but in fact these linear functionals are just of the form m times x, where m is some real number representing the slope of the line. So for example, here is the linear functional where m equals 0. Here is the linear functional where m equals 1. Here is the linear functional where m equals 2. Now I'm going to define the conjugate functional. This is a functional on the dual space. It will be a function of x star, but that means as a practical matter, it will be a function of the slope m. And the definition of this is it's the supremum of the difference between the linear functional in the dual space and the function f of x that we started with. And what makes this interesting is that the supremum is taken just over the set C. And as often happens in this course, the supremum will frequently occur at the endpoints. So let's evaluate this conjugate functional for the easy cases where m is less than or equal to 0 and where m is greater than or equal to 2. If m is less than 0, there is the graph of our linear functional. It is always below the graph of f of x, so this difference can never be positive. The supremum, in fact, is 0, and it's achieved at the point x equals 0. So, if m is 0 or negative, f star of m is 0, and it's achieved there. If, on the other hand, m is large, then the graph of the linear functional is always above the graph of x squared. You say, no, it isn't. X squared will catch up sooner or later, but on the interval from 0 to 1, this graph is always above that graph. It gets farther and farther above, and in fact at x equals 1, the linear functional has the value m, f of x has the value 1, and therefore the maximum value is m minus 1, achieved at the other point, x equals 1. In between 0 and 2, we have an honest-to-goodness calculus problem. We have to maximize the difference between mx, the linear functional, and x squared, which is f of x. Take the derivative with respect to x, set it equal to 0. Solve for x, we find the maximum is at x equals m over 2. And when we plug in the value there, m times x is m times m over 2. X squared is equal to m over 2 squared. The difference is m squared over 4. So let's look at a graph of this conjugate functional. As a function of m, it's identically 0 for negative m. It is equal to m minus 1 and has a straight line graph when m is greater than or equal to 2. In between, it has the value m squared over 4, and it all joins up very neatly. Not only is this functional continuous, the derivatives even match up at the 2 endpoints. Now comes the fun. This is another convex functional, and we're going to take its conjugate convex functional. And the interesting discovery we'll make is that we get back the function x squared that we started with, and we recover its domain. So this is a case where the dual of the dual is equal to the original space, and we can represent any element of x star star simply by a real number. This is kind of funny because we're representing it by the number x, so we're thinking of x times m as a function of m where x determines the slope of the graph. Now what we have to do is figure out the conjugate functional. The conjugate functional is the supremum of x times m minus f star of m, evaluated for m in the domain of the conjugate functional. Well, the conjugate functional is defined everywhere, so its domain is minus infinity to infinity. And now let's figure out what happens if x is less than 0. If x is less than 0, there is our linear functional. It gets farther and farther and farther below the graph, so the supremum of this minus that does not exist. Similarly, if x is greater than 1, so we have x times m with a slope x that's greater than 1, this gets farther and farther above the graph of f star because the graph of f star has slope 1. This has a slope greater than 1. So this time, as m gets more and more positive, we see the supremum does not exist. Check both cases. For the case of negative slope, this graph gets arbitrarily far above the graph of f star for negative m. That's why the supremum doesn't exist. In this case, it gets arbitrarily far above the graph of f star for positive m. In between 0 and 1, however, we have another honest-to-goodness calculus problem. And what we do is we write down xm, the linear functional, minus f star of m. And in between 0 and 1, we have a formula for f star. It's minus m squared over 4. We differentiate with respect to the variable m and get x minus m over 2 equals 0, and we discover the maximum is achieved when m is equal to 2x. So what is the conjugate functional, which I'm calling phi? It's x times m, x times the value 2x at the maximum, minus m squared over 4, 2x squared over 4. That's 2x squared minus x squared, or x squared on the interval from 0 to x to 1. So amazingly, we have reconstructed from the conjugate functional both the functional form of the original f and the domain that we specified. Now, in fact, this was known back in the 19th century. As was the case with many of the great mathematical discoveries of the 19th century. It was found in the context of physics. There are two famous alternative formulations of Newtonian mechanics. One, the Lagrangian formulation, where things are functions of position and velocity. And the other, the Hamiltonian formulation, where things are functions of position and momentum, which can be obtained by taking the so-called Lagrangian function and taking its derivative with respect to velocity. And it was well known in the 19th century you could translate back and forth between these two things. In fact, in modern language, the Hamiltonian function is the conjugate functional of the Lagrangian function. This also showed up in the context of chemical thermodynamics. In chemical thermodynamics, one can express the energy of a system as a function of its entropy, S and its volume, but it's frequently more useful to express the so-called Helmholtz free energy in terms of volume and the absolute temperature, which is the partial derivative of energy with respect to entropy. This is yet another example of conjugate functionals, and in this context, the transformation that takes you from one to the other and back is known as a Legendre transformation. We're going to be applying this in a more 20th century style where the functions involved are not necessarily differentiable. That's the end of this video. Enjoy the rest of your Thanksgiving weekend.